option. Last class for the hello. Yeah. Last class for the plate girders. In the plate girders, we had I think checked till the shear buckling of web using simple post critical method. Yes. Did I? This one. Check for the shear buckling of web using simple post critical method. In the IS code, I showed you. Mm, Why? I am having problem here connecting this hard disk. Where is my connecting? Okay, whatever. I'll leave this to find this IS code. But we have done till here. Um, This one we have done till here the check of the shear buckling of web using simple post-critical method from clause number 8.4.4.4, page number 59. Here we had done this. To find out this, you had to calculate this, then lambda, then to calculate lambda, you have to know tau b. To calculate tau b, you have to know your this, and then we have got what? Our this shear was greater than the shear which was calculated. Okay, so our design was okay. Now we had done this shear buckling. I think we will check till here the shear and the moments for the moments. Okay, the later stages you will get to know the other things. Then today let us go with the today let us do a problem on rectangle the tanks. Okay, water tanks. So basically in water tanks, okay, Basically, in water tanks, you will have this kind which is resting on the ground. Your water tank, you have seen, it can be rectangular tank, it can be your circular tanks, and then these are the water tanks which can be above the ground, on the ground, above the ground, below the ground, on the ground, below the ground, above the ground, here elevated. So we have we'll design a simple basic on the ground rectangular water tanks here for your seventh semester. So we have what? There are two conditions, okay, for your when you're designing a water tank. Okay, so that conditions are what? That conditions are this one. If your L by 2 is less than 2, this one, L by 2 is, if L by 2, this one, if your L by 2 is less than, sorry, L by B is less than 2, then what we do, we design the top continuous frame and the bottom, which we'll design, right? This is the top and this is the bottom of suppose rectangular tank. If I'm talking, then the top portion we are going to design as a continuous frame and the bottom we will design it as a cantilever. Okay, because here it is fixed and here it is moving kind of thing, so it is acting like a cantilever. So we'll design this portion as cantilever and this as a continuous frame. So when it is, okay, if I'll do this. So what happened? If your this is if your L by B is less than 2, what happens? The top continuous frame and bottom should be designed as cantilever. Okay, top should be designed as continuous frame and bottom should be designed as cantilever. Okay, now when your L by B ratio is greater than 2, then how you're going to design your rectangular tank? You will take the long wall as the cantilever. Okay, and what you'll do is long wall you're going to do that, and the short wall which you will have, and the short wall, there also in the short wall there will be two portions, which is your top and the bottom, right? So in the, suppose this is the short wall, now here at the top and bottom you'll have, so capital, suppose if this is your capital H, if I say this portion is your capital H and your this portion bottom three at a distance of H by 4 is your bottom portion, we are going to design it separately. So if this is your H by 4 here, so your this portion is how much? Capital H minus small h by 4 will give you your this distance, this height. So your this small h, which can be taken as small h, okay, this portion will go now, that's why I don't want to. Okay, I'll take here this pencil. Okay, if I consider this, okay, if I consider this to be capital H, okay, and this to be H by 4, this portion will be how much? Capital H minus small h by 4 will be this, which you can consider it to be small h. Okay, so now when you have this condition, when you have this condition, L by B ratio is greater than 2, then what you're doing, there will be, in a rectangular tank there will be a short wall, a long wall, Okay, so the short wall here, long wall you're going to design as cantilever, and the short wall, what you're going to do, this portion small h will be designed as cantilever, and this capital, okay, h minus small h, this is small h, okay, sorry, this one. If small h is equal to h by 4, then this portion will be capital H minus small h, which is this. So this will be designed as slab supported on a long wall. Okay, this is the short wall we are designing. So the top portion will be designed as a slab rest supported on a long wall. When we'll do the problem, you'll come to know. Let us take a problem here, a simple problem on the rectangular water tank. So what does the, okay, so design a rectangular water tank for the following data, for the following length 6 meter, okay, width of the water tank is 4 meter, okay, and the depth of the water is 3.5. Depth of the water, okay, it is 3.5. Tank rest on the ground. Assume M30 concrete and Fe415 grade of steel. So you have, we will consider M30 concrete and Fe415 grade of steel. So now this is your, suppose the tank here, the height is mentioned to be how much, height of the water is given to you. Suppose this is the tank, which the height of which is capital H, and this is your water, this is your water. Now the water level is given to be, height of the water is 3.5. So that means this is your 3.5, this one, this one is your 3.5. Okay. So now if we keep a free board, what will happen? See here, if we keep a free board here, we will always keep a free board for the tank. Okay, in a tank we always keep a free board so that when there is so that the water tank can carry some more water when it is required sometimes. Otherwise, if we keep this much only the height, there will not give any free board, what will happen, the water may overflow. That's why we keep a free board, always a minimum free board of 200 mm. So let us consider this to be 200, 150 or so you can keep, or 200. So we have captured 200. Length is given to be 6 meter, it is mentioned you here in the question, 6 meter. The width is how much? 4 meter. 4 meter. Depth of the water tank is 3.5. Now, once we know the depth of the water tank, this is our depth of the water tank. So, here we will have a freeboard of 200 mm. We have taken 200 mm here. So, now the total height we can find out, this total height. So, that will be how much? 3.5 plus 0. Here, this 200 mm. So, we got it to be 3.70. Okay, meter. Now we will check the condition, these two conditions which I told you, L by B ratio. So now after knowing this H, we will find out what is our L by B ratio. So L by B ratio, our length and breadth was given to us. So now when we have this, we got how much, the ratio of L by B is 1.5, which is less than 2. So what we are going to do, this one you see here, this is the first condition, which is L by 2. If it is less than 2, what we were supposed to do, we were supposed to design the top portion as cantilever. Okay. um Suppose at this, so the top portion is designed as cantilever, we will design, and the bottom should be designed as, oh sorry, this, the bottom portion will be designed as cantilever, this one, right? Okay, this is wrong. The upper portion will be designed as continuous frame. When it is less than, your ratio is less than 2. Okay, so this top portion will be designed as a continuous frame. Now you will check here L by 2 ratio. What is our L by B ratio? L by B ratio is 1.5, which is less than 2. So we will be designing it as the according to the first condition. Okay, which is the top portion will be designed as your continuous frame and the bottom portion as the cantilever, which is resting on the ground obviously. So this is fixed here. This one. Okay, so now you see here h by 4 distance, which is this h, small h. We will find out what is this distance, which is acting as cantilever, and the top portion obviously is going to act as a continuous frame. So we will find out the height up to which it is acting as a cantilever. So that height is h by 4. So that h by 4 is how much? Now our h is total 3.70. So that divided by 4, we will get how much? 0.92. Okay, so which is less than 1, so we will consider it the bottom portion. 1 meter of wall will be designed as cantilever, because there should be minimum, this should be minimum 1 meter. Your small h should be 1 meter. Okay, so this should be minimum 1 meter. Okay, not less than 1 meter. So we are considering this to be h by 4. We have got 0.925. So what we are doing, we are considering it to be 1 meter. Okay, so the bottom, that means what? Now this h, small h, right? This small h, which is small h is capital H by 4. This portion will be designed as cantilever, which is acting as a cantilever. And you have here the upper portion, you will be designing as what? You will be designing it as a continuous frame. Now if we see, we have the bottom portion it as a cantilever. Now there will be some design constants. Okay, for that you will require IS 3370 part 2 2009. I don't have here with me now. This hard disk is also not working. So we will you can note it down somewhere, like is 3370 part 2 2009 we will be using. Now if we consider this, we have considered our age to be 1 meter, right? This to be 1 meter. Now design constants will be how much? Design constants will be according to clause 4.5.2.2 table 2 and 4 of is 3370. is 3370 part 2 is how much? 2009 part 2 part 2 is 2009. Okay, part 2 2000, this is 2009. Okay, so from this code, okay, and table number yeah, this one 4.5.2.2 table 2 and 4, you will get what? M30. You will get the values of M30. If I could show, let me, let let me show if I can download this IS code here now. IS 3370 part 2 2009. IS 3370 part 2 2009. Yeah. This one. This is this. class number. Yeah, this one. I was talking about this. Okay, the this table 2 and table 4 here. This table, this one. Table 2 and table 4. Okay, so here you see, yeah, design of clause number 5.4.5.2.2 table 2 and 4. So here what we have to do, we have to calculate, there are some formulas. So I call, but to know that formulas, and to you have to know the formulas, and then you have to place the calculate the values. So for that, before that, we will need to find out the value of sigma cbc. Okay, the sigma cbc, the permissible stress, okay, in compression, and sigma SF. Okay, which is here you can see this one, permissible stress in concrete, permissible stress in steel reinforcement fostering. Here we had taken the grade of concrete to be M30. This one here M30 you see here. So that is how much? That is sigma CBC value. If you see, it is 10 here for bending. This one, and for bending we will consider. So M30 is 10, and we have what, sigma ST, the steel, the permissible stress in steel, is given by 130. This one, high strength, we are using high strength deformed bars, and in the tensile stress, type of stress in the cylinder. Okay, tensile stress in members under direct tension, bending and shear. So this was for compression, we have already taken. So in tension we are taking from here, the permissible stress in steel is 130. For the high strength deformed bars, we are not using this plain round mild steel bar, so we are using high strength deformed bars. So we got the value of sigma cbc from here for M30, and for M30 this one, the uh, sigma st. Okay, so once we got these values, this one 10 and 130, what we'll do, we have to calculate some formulas. Okay, first of all we will find out the modular ratio. Okay, why? Because we have to, using this modular ratio, again we have to find out the neutral axis coefficient. Okay, and why we are finding neutral axis coefficient? Because it is associated, or it is related to the lever arm coefficient, which we have to find out. And then this lever arm coefficient, why we are finding out? Because we have to find out the moment of resistance factor. Okay, the moment, mainly the, to calculate this moment of resistance factor, we need to calculate the rest of the things. So here moment of resistance factor is half into sigma cbc. We have known now sigma cbc, sigma cbc into k into j, where k is your neutral axis coefficient and j is your lever arm coefficient. So we will find out this, to calculate this neutral axis coefficient, what we have, the formula is k is equal to m sigma cbc by m sigma ck plus sigma ct. Okay, for that we need m here, again modular ratio. So modular ratio, we know the formula of modular ratio, 280 by sigma cbc, 3 sigma cbc. Okay, 3 sigma cbc. So m is equal to 280 by 3 sigma cbc. So 280, and sigma cbc is how much? 10. We have this one sigma cbc from S code, we have got this to be 10 Newton per mm square. So we have used this, and we got our modular ratio to be 9.33. Okay, now getting this modular ratio, we can find out this neutral axis coefficient. Neutral axis coefficient, we know our m value. M is how much? This one, 9.33. Sigma cbc, we know it is 10. M again, we know it is 9.33 here. Sigma CBC. Again, sigma CBC, we know sigma ST. This is ST. Sigma CBC. Okay. So these values are known to us, sigma ST, sigma st, sigma st, sigma cbc, sigma cbc. Okay, so we have calculated the neutral axis coefficient, which we got it to be 0.418. Now using this neutral axis, we have what? The lever arm coefficient. So what is our lever arm coefficient? That is given by 1 minus k by 3. Now k we have already calculated here 0.418, so use just the value of k and find out the Leverhulme coefficient, which comes out to be 0.861. Now using this Leverhulme coefficient, you can easily calculate your moment of resistance factor. Okay, the moment of resistance factor is how much? Given by half into sigma cbc into k into j. That means this k, this j, and sigma cbc for moment of resistance. So if just put out the values here and you will get your q value, which is your moment of resistance factor. Okay, with the help of this, why we are calculating this moment of resistance factor? Because with the help of this, thickness of the tank will be taken. Okay, so now you see we have calculated the values here. M30, all these values we have got. M30 how much, M sigma cbc, M sigma st. Okay, so now what we'll do is continuous frame action. This is continuous. First of all, we will check the continuous frame action. What was that? Why we are checking that? Because our top portion should be designed as frame. So continuous frame action. Okay, so continuous frame action ACTN. Okay, so here water pressure at this depth H by H minus capital H minus small h. This is capital H minus small h. That means here above this, from here to till here, it is how much? We will find out the pressure of water. Okay, on this portion. So that is given by how much? Obviously, it will be, you know, these things, gamma W into H. And what is the H at? Because since we are designing the top portion as continuous frame, so we will be finding out how much pressure is there continuously on that top portion frame. So continuous frame. So that is W is equal to gamma into H, and H is how much? Capital H minus small h, that our top portion. So we have got our pressure acting how much? 27 kilonewton per meter square. Now we will find out the final fixed end moment. Yeah. So suppose this is the plan of the rectangular tank. This is your length, the longer wall. This is the shorter wall, 4 meter. This is the longer wall, 6 meter. Okay. So now your moment, fixed moment will be how much? F A B C D. This is A, this is B, this is A, this is B, C, D. Now, this side, if we consider this side to be F, this to be E. Okay, here the pressures which are constantly on the walls. So the fixed moments will be how much on these walls? We have M, fixed moment at FAB. FAB. Okay, FAB will be how much here? That is given by minus PL square by 12. Okay, PL square by 12. And what is your P? Your P pressure is how much? This one. This water pressure comes out to be 27. So 27. And what is the length which is acting on it? The length which it is acting on it is how much? For M, FAB, FAB is this 6 meter. So 6. Okay. Now FA D, F A D. This is A B C D. This is your F. This is your E. 6 meter, 4 meter. Okay, now we will see clockwise. This one was what? Anti-clockwise. This one FAB. Now we will go FAD. Here FAD. FDC. AFD, this shorter direction we'll see now. In the shorter direction, our it is what given by P b square by 12. And what is your b here? Your b is this one, 4 meter. Actually this is pl square only. Here also it is pl square, but now since we are taking the shorter direction, 4 meter, here the fixed end moment here fab. So here the your how much will be the moment? W pl square, and l is now here this one, 4 meter. So pl square by 12 will be 27 into 4 square by 12. So it is 36 kilonewton meter. Okay, so again after that, once we have calculated the fixed end moment, we can do the distribution factor, and then we can find out the moment distribution. Moment distribution can be done. These things you have gone through in your analysis also, moment distribution factor, etc. So in this way, using this, we'll find out the depth, etc. Okay, so design the long wall. We will design the long wall, we'll design the short wall, and the distribution steels also we will provide. Okay, now